All right, scholars. I am back, this time at 11 a.m. instead of 11 p.m., so much more with it today. Still in my cozy clothes, though. Hope you are too. So once again, I apologize for my appearance, but this is the best you're going to get of me. So we need to move right along and begin discussing kind of our last bonding idea. We've been in covalent bonds. Let me remind you, everything we've been discussing applies to molecules, right? Covalently bonded groups of atoms. Same thing applies here. We're focusing in on covalent compounds, on molecules, and we're discussing something really important, and this should be brand new to everybody. And this is known as hybridization theory. Hybridization theory is once again, there's a way to visualize it. If you're a visual person, if you feel like you have a really good grasp on electron orbitals and what an orbital is and what the different orbitals look like, y'all remember the S and the P orbitals. If you have a good grasp on that, then this is going to make pretty good sense to you. If you don't, you're just going to have to memorize it. And I'm going to boil it down just incredibly simply, and it should not be difficult to memorize at all. After I do the simple bit, I will go into the detail, and I'll leave it up to you if you want to know the detail. So let's begin just with the definition. Hybridization theory is a way of visualizing or representing covalent bonds in which each atom involved in a molecule organizes its valence electrons into brand new hybrid orbitals which it utilizes for bonding. So first of all, we need to discuss and go over what an orbital is. Hopefully you remember that an orbital is a three-dimensional region of probability around the nucleus where an electron could be found, right? And so we've kind of skimmed over this and we hadn't really thought about this, but it is worth thinking about. In covalent compounds, we know that the electrons are, the valence electrons are distributed in different groupings and different domains for the atoms. And we know that a covalent bond is defined as a shared pair of valence electrons. Well, where are those electrons being kept? Where are they being held? In what orbitals? Hybrid theory tells us that when an atom bonds, it actually utilizes new orbitals. It utilizes hybrid orbitals to put those electrons, to put the shared or the unshared electrons. So remember that our orbitals, we have S-type, P-type, D-type, and F-type orbitals. Let me remind you that S, so this isn't like what it normally does. An S orbital, an S-type has one orbital for it to hold two electrons, right? And it's shaped like a sphere. The P-type sublevel has three different orbitals. D has 5, F has 7. We're not going to get into D and F with this, so just S and P. And remember that the P kind of looks like a dumbbell, and the three different P orbitals, I guess I'm already getting into too much detail here, but remember they kind of look like this. There's an, well, excuse me, I guess I should do it in the order. There's an X, so one that's kind of along the X-axis. There's a Y, one that's along the Y-axis, and there's a Z. So imagine this coming out of the screen at you. So these are orbitals, right? The p sublevel has 3 different orbitals. The s sublevel just has 1. And these are regions around the atom where electrons could be found, right? Regions of 3-dimensional probability, described by the Schrodinger wave equations. So what I'm telling you is that sometimes when an atom bonds, when it undergoes covalent bonding, it's going to use like brand new orbitals. It's not going to use an s or a p. It's going to use brand new, what we call hybrid orbitals. So I guess that, let me think about how I want to talk to you about this. I'll start with the simple, easy thing first. So here's the simplest way that I can explain this to you. If an atom has 4 electron domains, remember what an electron domain is. That's just anywhere around the atom in our Lewis structure where electrons show up at all. If an atom has 4 electron domains, it will utilize what we refer to as sp3 hybrid orbitals. So let me explain to you what sp3 means. Here's the idea. The atom in the molecule has 4 regions around it where it needs to hold electrons. It needs 4 brand new orbitals to do that. I'm going to make a little energy diagram. Going up my diagram represents higher energy levels. So here is an s orbital. It could be 2s, it could be 3s. It's just the valence s. And then here are my p orbitals. We've just said that, hey, our atom in question needs 4 different places to hold electrons when it's in this molecule. So what it's going to do is it's going to take its s sublevel, its s orbital. It's going to take 3 of the p orbitals. It's going to hybridize them. So P represents a little bit higher potential energy. S is a little bit lower. That's why they're oriented like this. So this is what the atom would do on its own, right? It would just hold, like when the atom is not in a molecule, it would have some P electrons, some S electrons, just chilling out. But when it's binding in a molecule, everything I'm talking about is specific for covalent bonding, for when an atom is in a molecule. It now needs 4 places to hold electrons that, for complicated reasons, need to be all of the same energy. We know from experimentation that these 4 regions have the same energy. The S and the P here have different energies. So what it's going to do is it's going to hybridize. To hybridize means that you smush things together, right? So it's going to create 4 brand new orbitals for bonding. Notice where I've put this energetically. It's not as high in energy as the P sublevel. It's not as low as energy in the S as the S sublevel. It's in between. Because what has happened is that the atom has taken 3 of its P orbitals, smushed it together with its 1 S orbital to create what we call sp3 orbitals. So these are 4 orbitals, and it's like we're giving them a name. It's like they belong to a brand new sublevel that we call sp3. Why do you think it's called sp3? Because we have hybridized the S and 1, 2, 3 p orbitals, sp3. And now it has 4 equal energy areas to hold electrons for bonding. I hope that makes sense. Let's look at a very simple example. When I do the Lewis structure for CF4, we all know it's going to look like this. I know that, I could say lots of things about this. You guys should know lots of stuff about this. We know that it's tetrahedral because it follows an AX4 pattern. We know that the carbon, I'm just listing things that I know. I know that the central carbon has 4 electron domains, 4 regions where electrons show up at all. And I also know that each of the fluorines also have, that's bad grammar, each has 4 electron domains. Because think about it, each fluorine here will have 4 places around it where electrons show up. Okay. Typically, when we look at hybridization, we're only going to be worried about like the central atom. But technically speaking, these fluorines are hybridized as well because they have 4 electron domains as well. Anyway, so we would say this, that the central carbon we could say it utilizes or it has sp3 hybridization. What does that mean? It just means that it needs 4 equal energy regions to hold electrons. And we call those brand new orbitals that it uses just for bonding. We call them sp3 orbitals. So it's using 1, 2, 3, 4 sp3 orbitals. They are brand new orbitals hybridized from old atomic orbitals, and they're used just for bonding. How do we feel about that? So what I'm telling you is quite simple. If an atom has 4 electron domains, it's always going to be sp3 hybridized. And it's just that easy. Another way of thinking about it is, hey, if it's tetrahedral, it's going to be sp3, right? So all of these things right here, I'm telling you, they're synonymous. They mean the same thing, okay? Okay, let's look at another example. Well, okay, so I'm still going through like the simple way, and I'll make this a little bit more complicated in a moment for those of you who care, but this is really all you need to know. All right, so next I want to tell you that if an atom utilizes 3 electron domains in the molecule, we're talking about atoms in a molecule, then it will utilize sp2 hybridization. What does that mean? That means that when in a molecule, the atom needs 3 equal energy orbitals to hold electrons. It just needs 3 of them. So it's going to take 1 of the s. It's going to take 2 of the p, because I just need 3 orbitals. That's all I need. And I'm going to create 3 equal energy orbitals, which I call sp2 orbitals. You'll notice that I'm going to have 1 leftover unhybridized p orbital. Because I've only needed to take 2 of them to hybridize, right? I've hybridized 1s, 2p to get me 3 regions where I can put electrons for bonding. And I'm going to have 1 leftover unhybridized p orbital. That will be important later when we get into the more complicated analysis of this. But for now, all you need to know is that if any molecule, let me think of a good example. Well, here's an example. The carbonate polyatomic ion. If I did the Lewis structure for that, it ends up looking like this. I'm going to go ahead and do the lone pairs. And you can see that this is AX3. That's trigonal planar. And so I would say that the central carbon utilizes sp2 hybridization. Whoops. And I'm realizing that I wrote something earlier that's going to throw you off, so I apologize. This needs to be modified up here. Sorry. I don't want to confuse anybody. This name right here, it is the name of this shape, right? It is tetrahedral. This one down here is actually trigonal planar, but that's also like the name of the family that they belong to, if that makes sense. This is a molecule in the trigonal planar family. This is a molecule in the tetrahedral family. So it's those parent geometries or the families that I'm referring to. If that confuses you, just remember what I'm saying about the electron domains. Hey, if there are 4 electron domains around an atom, it's going to use sp3 hybridization. If there are 3 electron domains around an atom, it's going to utilize sp2 hybridization. Another way of thinking about that is, hey, if the molecule belongs to the tetrahedral family, it's going to be sp3 hybridized. If the molecule belongs to the trigonal planar family, then that central atom will be sp2 hybridized. Now, I could also number the oxygens. And I could say something like this, that I could say that oxygen number 1 utilizes sp2 hybridization. But oxygen number 2 and 3, they utilize sp3 hybridization. So hybridization is unique for each atom. Notice how I'm talking about the hybridization of the atoms, not the molecule itself, but of the atoms in the molecule. So let's look at this first oxygen. This first oxygen there's 1 electron domain, there's 2 electron domains. Remember, the double bond just counts as a single electron domain. So this oxygen here has its electrons organized in a trigonal planar parent geometry, 3 electron domains. That's sp2 hybridization. Look at the other oxygens, though. They have 4 regions around them where electrons show up. So they're going to utilize sp3 hybridization. I hope that makes sense. Next, you all need to know that if an atom has 2 electron domains, it will utilize sp hybridization. So in this case, to make its hybrid orbitals it uses for bonding, it's going to take the s orbital, one of the p orbitals. It's going to make two brand new orbitals for bonding that we call sp orbitals. And then just like last time, I'm going to have two, leftover unhybridized p orbitals. Because I've only had a snap of them. It's sp. We could s1, p1, one s orbital, one p orbital. We hybridize to make a new p orbitals, two of them that we use just for bonding. So let's look at an example of this. We do the Lewis structure for carbon dioxide. This is one that you all should have memorized, really. It's going to look like this. And this is linear, right? So I'm going to say that the central carbon, it has two electron domains, 1, 2, regions around it where electrons show up at all. So I'm going to say that it utilizes sp hybridization. What if I was worried about the oxygens? The oxygens, they both utilize what? What kind of hybridization do they utilize? Well, they each have 3 electron domains, 1, 2, 3. And you guys know that's sp2 hybridization. Okay, that's it. That's quite simple. Now I want to tell you some why don't we do some more examples here? Actually, let me tell you some facts. According to this theory, single bonds result from the direct head-on overlap of orbitals we call that a sigma style bonding. So really simple, you need to know that single bonds, we call them sigma bonds in this theory. I'll explain what I mean by the overlap thing later. You do need to know it, but you don't really need to understand it unless you're just curious. I'll explain it in a moment. According to this theory, double bonds result from one sigma bond and one what we call a pi bond. And let me define a pi bond for you. A pi bond is a bond that results from the indirect interaction of leftover unhybridized p orbitals. Simply put, a pi bond is indirect. It's not like a head-on overlap like a sigma bond was. The important thing you need to know, very simple to memorize, a double bond is one sigma and one pi bond. Let me go back up to carbonate here. I noticed that carbonate has a double bond right here. I would say, hey, that double bond is composed of a sigma bond and a pi bond. That's true for all double bonds. If you want to kind of understand this on a deeper level, well, we said the central carbon utilizes sp2 hybridization. That means that it has one leftover unhybridized p orbital. This oxygen, number one, is also using sp2, so it also has a leftover unhybridized p orbital. The double bond here comes from the fact that the carbon and the oxygen, they have one of their orbitals that directly head-on overlaps one of their sp2 orbitals, but then they each have an unhybridized leftover normal p orbital that's going to interact indirectly, and that's called a pi bond. So the fact that they both have sp2 allows them to form that double bond, allows them to form the pi bond. Think about this. This compound had no double bonds because it has no leftover unhybridized p orbitals to form a pi bond. So this should start to make pretty good sense to you all. It's all kind of coming together. The structure, the shape, the hybridization, it even goes into what kind of or a single bond that the molecule can have. Here, there's a double bond between the carbon and the oxygen because this oxygen is sp2 hybridized. It has a leftover p orbital. This carbon has a leftover p orbital. Those can interact and make what we call a pi bond. All right. And then finally, I'm going to say, according to this theory, triple bonds result from one sigma bond and two pi bonds. So any atom that triple bonds it's got to have, remember what a pi bond is? It's the interaction of leftover unhybridized p orbitals. If we're forming two of those to make a triple bond, any atom that triple bonds must be utilizing sp hybridization because that's how we're going to get those two leftover p orbitals to form our two pi bonds. So let's look at some examples. In each of these, I want to describe let me just think about in each of these molecules, I want to figure out the shape, the structure. We've done all these before. And then I want to describe the hybridization and the bonding on every atom. So let's do one, and you will see what I'm talking about. NH3, let's do that one. Ammonia, everyone knows it's the best molecule that exists. I know right away it's going to be trigonal planar, just like that. And so I look at this and I recognize, aha, that nitrogen has 4 electron domains. I'm sorry, I said earlier it's trigonal planar. That is incorrect. It's trigonal pyramidal. So there's many ways that you can start to think about this. I'm going to say that the nitrogen utilizes sp3 hybridization. How did I know that? It has 4 electron domains. That's one way to know. Another way to know is that it belongs to a tetrahedral parent geometry. It's trigonal pyramidal, but that's like a modification of tetrahedral, right? It has that lone pair. So that's it. What about the hydrogen atoms? Well, Think about it, y'all. What kind of electrons do hydrogens have? Just one s. They don't even have a p sublevel to hybridize with at all. So they don't hybridize. Hydrogen will never hybridize. So it just utilizes its normal s orbitals. How about the bonding? Well, I see 3 single bonds. So I know that there are 3 sigma bonds in this molecule. I would call each of these a sigma bond. Sigma, sigma, sigma. And that's pretty much it, my friends. All right, our next one is CO, carbon monoxide. This one's worth memorizing if I were you. Carbon monoxide utilizes a triple bond like this. So let's talk about each of these atoms. I'm going to say that the carbon utilizes, what do you think? You have a 33.33% chance. Is it sp3, sp2, or sp? What kind of hybridization? Just count the electron domains. Carbon has 2 electron domains in this molecule. So carbon is going to utilize sp hybridization. How do we know that? Because it has 2 electron domains. I can also think to the fact that the electrons are arranged linearly around the carbon. The oxygen is the exact same. Same reasoning. What about the bonding? Well, I see a triple bond. I know the triple bond is always 1 sigma and 2 pi. And there, we've analyzed the hybridization and the bonding of this molecule. Now, for those of you who are really curious about this and who are really kind of tracking with me, you will recognize, oh, of course it has 2 pi bonds, because this carbon here, it has sp hybridization. It has 2 leftover unhybridized p orbitals. The oxygen does as well. So because they both have that, they're both going to be able to form a pi bond with each other. 2 pi bonds, 1 pi bond for each leftover unhybridized p orbital. Carbon has 2 leftover unhybridized p orbitals. So it's able to form 2 pi bonds, and so is oxygen. So they're able to form 2 pi bonds with each other. I'm not saying they form 4 pi bonds. I'm saying they're able to form 2 pi bonds with each other, okay? Whenever I kind of draw this out and show you visually what's going on a little bit later, I think it may make more sense. Okay, acetic acid is next. We've done this about 1 trillion times. I am going to go ahead and draw the lone pairs around the oxygens just so y'all can see. So let us think about the hybridization here. Of course, all the hydrogens don't hybridize at all. So I'm going to say that all the hydrogens use their normal s orbitals. And let me number these. Let's make this carbon number 1, carbon number 2, oxygen number 1, oxygen number 2. We want to talk about how those atoms are hybridized. So how about carbon number 1? What would y'all say about carbon number 1? I feel like the host of a children's television program right now. What? You found a clue? Where is it? What would you say about the hybridization for carbon atom number 1? Good job. It's sp3. How do we know that? It's got 4 electron domains. We also know that it's tetrahedral, belongs to the tetrahedral parent family. Anything that belongs to a tetrahedral parent geometry utilizes sp3. How about carbon number 2? Should be really simple. You should be able to tell me this right away. It's sp2. How do we know that? It's utilizing 1, 2, 3 electron domains. I also recognize that it's Trigonal planar. Anything that belongs to the trigonal planar family is sp2. All right, almost done. How about oxygen number 1? Well, it's going to utilize sp2 as well, because once again, it's got 3 electron domains. And I would describe like this shape over here as linear, because that's where my mass is. My atoms are actually in a line. There's only 2 atoms there. But in terms of its electrons, this oxygen is distributing its electrons in a trigonal planar fashion, right? It's got 3 places to put its electrons. So once again, anything that belongs to the trigonal planar parent family is going to be sp2 hybridized. Finally, oxygen number 2 utilizes, you guys tell me, sp3 hybridization, because it's got 4 electron domains, 1, 2, 3, 4. It belongs to the tetrahedral parent geometry family, doesn't it? It's bent. It's the tetrahedral version of bent, right? 4 electron domains, but 2 of them are lone pairs. Anyway, okay. Now let's describe the bonding. I'm going to do this a little bit differently. I'm going to draw all of the sigma bonds in red. You can label them, you can count them, whatever you want to do. I'm just trying to describe the bonding. Well, I know that everywhere there's a single bond, that's a sigma bond. And a double bond consists of a sigma bond. So I have 1, 2, 3, 4, 5, 6, 7 sigma bonds. And then how many pi bonds do I have? I have 1 pi bond. Now, you should all be having an aha moment right now, hopefully. The location of the pi bond should make perfect sense. Why is it that the carbon is able to pi bond with that oxygen? Because they're both sp2. They both have a leftover unhybridized p orbital to interact with each other and form that pi bond. Okay, so I hope that made sense. And I don't want to confuse you. Me drawing one of these lines as a sigma and one as a pi, that is not fully correct. Really, what I should be saying here is that like that double bond is a sigma and a pi bond. It's not like it's that one little stick is sigma and then another little stick is pi or something like that. It's a little bit more complicated than that. But anyway, I hope this makes sense. Okay, I think we got one more CO2. We did this earlier. The carbon is utilizing, or sometimes really just depends on how you want to talk about it. Sometimes we say it is sp hybridized, or it uses sp hybridization, something like that. How do I know that? Because it's linear. It's got 2 electron domains, 2 places around it to shove electrons, right? One on the left side, one on the right side. The oxygen atoms are sp2 hybridized, because they each have 3 electron domains. They would each belong to the trigonal planar family. We want to describe the bonding now. I see 2 double bonds, so I know that each of them are going to be composed of a sigma and a pi. So I have like 2 total sigma bonds here. I have 2 total pi bonds in this molecule. This should make perfectly good sense to you. Each of these oxygens is capable of forming 1 double bond because it's got 1 leftover unhybridized p orbital. It only used 2 of its p orbitals for hybridization. It's got 1 left over for a double bond. The carbon has two leftover unhybridized p orbitals. One of those is used to make this pi bond over here. The leftover one is used to make this pi bond over here. Okay, should we do another one? I think you guys hopefully got it. Okay, so hopefully that was simple. I know it's a little bit abstract, like talking about Mr. Thurman. What the heck does it mean for orbitals to hybridize? It's a bit complicated. It's based on Schrodinger's wave equations and things like that. But I think that this should make pretty dang good sense to you. So really, the moral of the story, my friends, is that if you know how many electron domains an atom has, you know what kind of hybridization it's going to use. All right, and it's really that simple. You know, every single bond is a sigma bond. Every double bond is 1 sigma and 1 pi. Every triple bond is 1 sigma and 2 pi. Okay, so now I want to make it a little bit more complicated, and really, you guys don't need to know this. Let me see if I can open. Let me save this. Okay, I'm going to open the PowerPoint. And you don't really need to take notes over this. It might just be helpful for you to listen. Ooh, I don't know if I have this in part 1 or part 2. I guess we're about to find out, my friends. If you feel like you got this, you can really just, turn the video off and go about your business. Or you can hang out. Why not? What else are you going to do, right? Okay, molecular geometry. I think I might have this in a part 2. I do. Ugh, okay. Please hold, y'all. I'm so sorry. So how are you? Y'all staying warm and cozy? I have so many friends in Texas right now who are just like, they don't got water, they don't have power, they don't have heat. It's like 30 degrees inside their houses. I feel so bad for them. But I think all this weather is behind us and we'll be able to move on with our lives. And I will finally be able to see you on Monday. Just in time for standardized testing. Yay. This program really has a hard time. Okay, so first of all, the only good photos of this I could find online had Arabic captions. So you can listen to this, or you can not. So this is describing sp3 hybridization. And remember how we said that that belongs to the tetrahedral family? In other words, it's got 4 electron domains. And we know that tetrahedral, that the tetrahedral family basically has bond angles of 109.5. But I want you to think about this. The s orbital and each of the p orbitals, they're like 90 degrees away from each other. And so this is part of the motivation behind why scientists realized that new orbitals had to be used for bonding, hybrid orbitals, because the geometry doesn't work. We study a tetrahedral molecule, and we know the bond angles are 109.5. A regular s and regular p orbitals will not get us 109.5 degrees. They're 90 degrees away from each other, right? Well, it turns out that if you take the Schrodinger wave equations that describe the s orbital, and you take the Schrodinger wave equations that describe the 3p orbitals and you smush them together into a new equation, they will describe these hybridized orbitals. Here's an sp3, 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 sp3. They will describe these hybridized orbitals, and guess what the angles are between them? It's 109.5, just like we need for tetrahedral stuff. All right. So that's the motivation behind all of this. That's how we know that atoms use brand new orbitals for bonding. Here's what I was talking about earlier. We've made 4 brand new orbitals for bonding, and they're equal energy. We call them sp3 because we've taken 1s, 3p orbitals and smushed them together. Okay, so here's a molecule, CH4. You know it's tetrahedral, and this is really helping you understand what a sigma bond is. So in blue, those are all of the sp3 orbitals of the carbon atom. Brand new orbitals it has kind of brought into existence just for bonding. And then these right here, just the hydrogen's boring little unhybridized s orbital, because that's all hydrogen has access to. So a sigma bond, what we're saying a sigma bond is now a single bond. We're still saying it's a shared pair of electrons. That's still what a covalent bond is. But sigma is specific about how it shares those electrons. Those electrons are going to be like trapped where the orbitals overlap. Because remember what an orbital describes? It describes like where the electrons are probably located. So if you have this overlap of probability, those electrons are going to be found there. So you can see that that bond, that sigma bond, that is a sigma bond. Sigma, 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 sigma. That is formed from the direct head-on overlapping of the orbitals, of the sp3 orbital for carbon and the s orbital for hydrogen. They just overlap each other, and that's a sigma bond. We could keep kind of talking about the same thing for sp2. Here's our leftover unhybridized p orbital. This is a molecule that is C2H4. If you do the Lewis structure for that, it's going to look like this. You guys should know right away that those carbons utilize sp2 because they have 3 electron domains. And so this image here is showing you the sp2, where right here I would get a sigma bond, sigma bond, sigma bond, sigma bond. Those are my single bonds with the hydrogens. And then there is a sigma bond that develops from the direct head-on overlap of the sp2 orbitals of each carbon. But because the carbons are just sp2 hybridized, they have that leftover unhybridized p orbital. Each of them have that. So here's the leftover unhybridized p orbital for that carbon. Here's the leftover unhybridized p orbital for that carbon. They're going to interact with each other and make what we call the pi bond. This is hard to visualize, but this p orbital of carbon has an electron in it somewhere. This p orbital of carbon has an electron in it somewhere. Those electrons will be attracted to the nucleus of the other one. And so we say kind of that the pi bond is like sort of spread out in space above and below the sigma bond. I know that's very abstract and wacky. So here's like a 3-dimensional picture of that. You can see the leftover unhybridized p orbital. What I'm telling you is that the pi bond, so here's the sigma bond of the 2 carbons. What I'm telling you is that the pi bond is sort of like above and below. It's this remember what I wrote down whenever we first defined it? It was an indirect interaction of leftover unhybridized p orbitals. So there you go. This is trying to show you the pi bond. It's above and below that sigma bond. All right. And then we can keep going with sp hybridization. So here's a picture of that. This is carbon dioxide, CO2, which we've already seen. We said that each of the oxygens will utilize sp2 hybridization. So they have 3 sp2 orbitals because they need 3 places to put their electrons. Carbon, though, is just going to use sp hybridization, 2 electron domains. Each oxygen, look over here in blue, that's the leftover unhybridized p orbital of the oxygens because they're sp2. They have 1 leftover unhybridized p orbital, right? This in blue, and maybe I should have slowed down on this, but this is 1 p orbital, right? A single p orbital has that dumbbell shape. It's not 2 p orbitals. So here's the leftover unhybridized p orbital of oxygen. Here's the one of this other oxygen. And then carbon has 2 p orbitals left over unhybridized because it just needed to hybridize one of them to make its sp. And then right here are those 2 leftover unhybridized p orbitals. So it's able to make a pi bond with that oxygen and a pi bond with that oxygen. And of course, there's our direct head-on overlap sigma bond. There is a summary of this in the slideshow. I sometimes use the phrase effective pairs. That's the same thing as saying electron domain. Same exact thing. You may want to go look at this summary slide in the part 2 of the PowerPoint. All right, so that has been hybridization. I'm going to post a homework assignment. You guys can keep going in the packet to work on this. I think there's lots of multiple choice questions that have just been unlocked for you, so to speak. I do want to point out, too, that on the well, I guess I can't open it, but on the big packet, the Unit 3 packet, the very first page that summarizes all the geometries, it summarizes this too. I've written like sp3, sp2, sp for all the different families to help you remember that. All right, y'all. Well, please email me with your questions. I hope that this made some sense to you. We got to keep trucking right along. We're probably looking at an exam. We really need to have one next Tuesday. I don't think it's going to happen, so probably Wednesday. But just please know that you all need to be working and working hard, and we cannot get any more behind in here. Oh, shoot. There's standardized testing next week. Well, crap. Well, I guess I'll figure out the exam date. Anyway, I'll be in touch about it. All right. Thank you. I will see you all later.